to the 56th session of the Porous Media Tea Time Talks. Today, seminar is dedicated to the China University of Petroleum, which will host an InterPore annual conference this year in Qingdao, so it will be next month. So today we will have the pleasure to hear from two junior researchers from this university. So Zijie Wang and Yifan. So Sarah and I'm joined in the studio by Madi, which is actually in the CNRS, and we are part of the InterPore Young Academy as members of the Porous Media Tea Time Talk team. So our first speaker today will be Yifan Li. So she is currently doing his PhD program in the China University of Petroleum in Qingdao, and her research interest is about the fluid distribution in nanopores. So yeah, and today she will talk about distribution characteristics of hydrocarbon in nanopores. So Yifan, the floor is yours. If you may share your screen, you can then start.
All right. So I'm going to share my screen for a second. Can you hear my screen right now?
Not yet.
I'm not yet?
No.
Present some share screen. This is my screen. Is that okay right now? You are in the show. Can you see my screen?
No, we can't see you. Please the present button on the bottom.
Couldn't see. Sorry for a second. What happens? Slides. Maybe I could upload my slide. Sorry for this.
I mean, the share screen option would be better, I guess. See if you can manage.
Present share screen. Share. Is that okay? What happened?
No, it's not. So I'm sorry.
I share my screen. Is that okay?
No. Okay, so we may shift the speakers down, and we will come back to you with Jenna. Right? Is it okay for you?
Yeah, it's okay. I'm gonna fix this technical issue. So okay.
So we will then start with Zijie. So he is also a PhD candidate, major in the same university, and he is working on the simulation study of in-situ conversion process in low-medium maturity shale oil reservoirs under the guidance of Professor Yongyao. And today he will talk about a couple THMC model for simulating in-situ conversion process in low-medium maturity shale oil reservoir. So please, go ahead with your presentation.
I'll share my screen.
Yeah, please. Okay. So we are seeing your screen, then perfect. So the floor is yours.
Okay. Thank you. Hello, everyone. I'm Zijie Wang from a PhD candidate from China University of Petroleum. Under the guidance of Professor Qingdao, my research topic is simulation study of coupled THMC simulation for in-situ conversion process in mid-low maturity shale oil reservoir. It's my honor to present the tea time talk. Firstly, I'd like to begin the research background. Shale series can be divided into oil shale, low mid, and high mid maturity according to the thermal maturity. Shale resource is widely distributed in China and is mainly of mid-low maturity. This kind of shale oil reservoir has low porosity and permeability. filled with returned hydrocarbon and unconverted solid organic matter. Therefore, horizontal drilling and fracture technology is insufficient to develop such reservoir, and the in-situ conversion technology is urgently needed. The in-situ conversion technology can be divided into electric heating, convective heating, autothermic pyrolysis, and radiative heating, according to the heating method. Here, we choose 4 representative heating methods: the SAP horizontal heating well, MTI, and TSA as a research target. Now I'd like to turn to the numerical and the schemes. Here we develop its involution, heat loss, and formation subsidence. Then the conservation equation and the OSD model are numerically discretated according to FVM and FEM respectively, and solved with the Newton-Raphson iteration method. To calculate the fluid properties, out and then followed by the phase splitting calculation. The VLE calculation module is very important in the multi-phase, multi-component mass and heat transfer model. Important parameters such as fluid density, viscosity, and enthalpy can be obtained. The chemical kinetic reaction model includes a series of multi-phase, multi-stage parallel reactions, including the decomposition of corrosion and the cracking of hydrocarbon. To improve the computation efficiency, pseudo components such as IC37, IT13, and IC2 are used to represent the heavy oil, light oil, and hydrocarbon gas. With the numerical model and schemes mentioned above, a simulator is developed based on Fortran, which can fully consider the physical and chemical processing during SAP, including the multi-scale, multi-phase, multi-component seepage, parallel chemical reactions, and the THMC coupling mechanisms. The simulator is consistent with CMG in black oil model and the compositional model, and are more accurate when simulates the chemical and the heating process. To evaluate the feasibility of SAP in shale oil reservoir, a 3-dimensional physical model is established as shown in the figure, including the shale formation, the overlaying and underlaying surrounding formation, well at the center, with four observation points showing. The basic parameters are shown in the table. From the physical variation patterns, we can see that during SAP, the overall temperature within the heating zone reaches above 580 Kelvin, and the corrosion pyrolysis rapidly. Solid organic matter fully consumed. As the temperature increases, the hydrocarbon cracking occurs and the gas saturation increases. From the displacement field, it can be seen that the displacement near the heating well is the largest, and the displacement field in X and Y directions shows symmetry. During SAP, the formation undergoes deformation under thermal expansion, compaction, and reaction strain caused by the pyrolysis of corrosion. From the relationship between corrosion concentration, porosity, and temperature, it can be seen that after 1,200 days, corrosion near the production well is completely consumed, and the porosity reaches a maximum value of 15%. From the production content variation of each component, it can be seen that Fe37 is the main component in the early stage. As the formation temperature reaches a corrosion pyrolysis condition, the proportion of Fe13 and Fe2 increases, and surpassing Fe37 at point A and B respectively. As the Fe37 cracking reaction process, Fe13 exceeds Fe2 after point C. As the Fe13 cracking reaction process, proportion of Fe2 increase after point D. In order to comprehensively compare oil and gas production, gas was converted to oil equivalent. Compared with depletion, the cumulative oil equivalent of ICP increased by 5.7 times. From the variation pattern of barrel oil cost, it can be seen that the production increases rapidly and the cost of barrel oil decreases, stabilizing at $30 to $36 per barrel. And how about large-scale SAP? In order to explore the feasibility of horizontal well electric heating technology, this section established a three-dimensional physical model, which includes a 10-meter shale formation and a 10-meter overlaying and underlaying sandstone layer. There are 11 horizontal production wells with a perforation section of 100 meters, and the heterogeneity of the formation is shown in the figure. At the same time, two development schemes are designed, among which Scheme 1 includes 20 horizontal heating wells and Scheme 2 includes 12 horizontal heating wells, with a heating section length of 100 meters and heating temperature maintained at 650 Kelvin. The temperature, organic matter concentration, and the gas saturation field in the SCP process of the two schemes are shown in the figure. It can be seen that in Scheme 1, the temperature within the heating zone reaches about 560 Kelvin, and the pyrolysis reaction occurs with corrosion completely consumed. When the temperature reaches 630 Kelvin, the hydrocarbon cracking occurs rapidly and the gas saturation increases, while the heating efficiency in Scheme 2 is lower than Scheme 1. From the comparisons of cumulative oil equivalent and barrel oil cost under two development schemes, it can be seen that the cumulative oil equivalent obtained from Scheme 1 increases by 69%, with the lowest production cost of $29 per barrel, which is better than Scheme 2. Therefore, for horizontal well electric heating technology, a multi-layer heating wells layout pattern can be adopted to improve the economic benefits. That's all about my presentation. Thanks for your listening.
Thank you very much for the presentation. Very informative. For people online, maybe they can type down the question in the comment section and we're gonna read it for Zijie. So meanwhile, I've got a question. Like, does it matter like what type of cryogen you've got into the reservoir, or is there any method that you can implement different, kinetics and dynamics for the formation of cryogens to petroleum in your model?
Sorry, I didn't quite understand.
Like different cryogens that you've got into the reservoir, does it matter what type of cryogens you've got, or?
In our research, we concentrate on the temperature field evolution and the corrosion pyrolysis, but we did not consider what type of corrosion. We use a more common reaction model.
All right. Okay. Thank you very much. And does it one more question. What's your take on different patterns that you can have for heating into the reservoir and the production well patterns? Is there any significant difference between different patterns that you can have into the reservoirs?
You mean the heating pattern?
Like the geometrical, like what we saw on the screen. Like I think for the heating you had like a hexagonal section, and then you had horizontal wells for the production. So does it matter if you change the geometry of the your wells? Does it have any great impact on the production?
In the sensitivity analysis, we have studied the heating pattern, the effect of heating pattern on the cumulative production. Here we only present a base study to see the single layer and the multi-layer heating pattern effect on the production.
Okay, thank you.
Thank you.
So I don't see any questions in the comments. If Sarah doesn't have any question, maybe we move to the next speaker. All right. So as already presented, the next speaker is Yifan Li. She's a PhD student in China University of Petroleum, and her research revolves around fluid distribution into nanopores. If you can share your screen, it will be great.
Yeah.
So the floor is yours.
Can you see my screen now? Yeah.
Yes.
So hi everyone, and I'm Yifan, and I'm currently doing my research in China Universities of Petroleum. Yeah. Thank you very much for the introduction, and thank you for the invitation to present my research online. So it's a pleasure to be with you today. And now I'm going to talk about my topic, which is the distribution characteristics of hydrocarbon in nanopore. Yeah, I'm going to start basically to describe one case of my topic. This slide is kind of an overview, and I will show one case for introduction just to see where kind of like the tool that I use here is molecular dynamic simulation, what the MD simulation could do in like exploring the hydrocarbon distribution. In this case, for alkenes in nanopores of our shale formation. So here we do. This is the outlines of my presentation. It's kind of our structure of this talk. I will introduce the research first, and I will introduce the background first, and then is the methodology that I apply in this study, and then some results and discussion is available to use, and finally some conclusion has been drawn. So we start by discussing the characteristics of shale rock that contribute to the confinement. As we know, productions of like hydrocarbon from unconventional reservoir is attracting like attention from oil and gas industry. There is a reason why we do this research, especially for those unconventional reservoir like shale formations or that Thai reservoir as well. So the picture shown here is the pore size distribution for like typical shale reservoirs of like Bacon shale rock here. So from this curve, we see the distributions of the pore size is a heterogeneous, right? So there's abundance like pores ranging from like 2 to 20 nanometer. According to some literature that I had read before, it tells up like the pore to like molecule size ratio. If the ratio lower than 20, that means the thermal and physical and the dynamic properties of a confined fluids might derive considerably from the bulk phase, right? Hey, can you hear me? All right. I thought I'm lagging right now. So So this is the reason why we do that. Like confined fluids may derive from the bulk fluid, right? So here is the pores of Marcos pore. As we see from this picture, the bulk phase of the fluids occupies a pretty large volumes of the whole pore space. So the thickness of the absorption layer, which is colored by yellow here, can be neglected. So compared to the Marcos pore, we see this nanopore. Within this nanopores, the hydrocarbon exactly it have be like comparable size to the interaction range between the pore walls and the hydrocarbon. So that means the pore wall attraction can cause heterogeneous distributions of hydrocarbon because they are like pretty thickness of the social layer. So we have to determine the confinement effects on the hydrocarbon. So let's move to the next slide. So the next slide is the methodology that I use in this study in this case, because generally we do some experiments on the fluids within cores. That means generally the experimentalists find some interesting observation, and their experimental on their measurements might lead them kind of in need of a more atomic resolution explanation, and that is what the simulation are for. Simulation could give more insight into the atomic scale process happening like within few nanometer, like this range of pores of in the shale formation. So that allows us to make a lot of things based on the nanoscale pore. So this is for our simulation. This is the nanopore model that I built for the mineral pores in the shale formation. I use the pure cordial pores as our nanopore, and then the graphene is used to present the organic matter within the shale reservoir. So for the hydrocarbon here, I use methane and pentane, and as well as the octane to represent those components within the nanopore. So after the nanopore models and the fluid model is established, we assign them as force fields, and we add certain numbers of fluid molecule into nanopore. And after the model preparation, we go to our simulation runs. Is here. So before that we should do the geometry optimization first to make sure that our module is stable, and then we apply the NVT simulation. That means we run our system with constant numbers of atoms, and the volume and the temperature also keep constant. And after simulation for equilibrium, allow times for equilibriums, and we get the continuous density distribution through the radial directions of our pore, and we could capture how those molecule within the nanopore, how they distribute them to capture the hydrocarbon property from atomic scale. So let's go to the results and discussion section. So here is the equilibrium configurations of our system, and along this direction is our radial direction, which I captured the mass density distribution of alkanes along the radial direction in this 5 nanometer cordial nanopore here. So from this curve, this dashed line is the bulk fluid density, and this solid line is the distributions of density that within the nanopores. As we can see from this curve, that the molecules within nanopore is attracted by the pore wall. As we introduce to the pore wall, the whole density distribution becomes heterogeneous. for those molecule aggregates around the near to the pore wall, they form the density packs, and those molecule within in the center, they are can remain quite constantly, and the density of that phase is less than the bulk phase. So according to the density so for bulk phase, we actually separate the nanopore, the fluid in nanopore into two phase, which is absorption phase and the free phase. So the density value for phase with ascending order could be acting like this. The smaller one is a density for free phase, another is the bulk phase, and the greatest one is for the absorption phase. So let's go to the next slide. And this slide, I present the absolute values of potential energy occurs for per molecule. As we can see from the graph on the left-hand side, the absolute values of potential energy occurs for our molecule. Is at the position which is quite close to the pore wall. That means molecule packed tightly here has some higher structural stability than those free phase molecule. So that indicates molecule are prone to aggregates on the pore wall to form a stable absorption layer with high density packs. From the energy point of view, large absolute potential energy indicates the high density value. Also, to understand that why the densities of free phase is exactly a lower value compared to the bulk phase, we have this table here. Let's see the potential energy of hydrocarbon in the nanopore actually is contributed by two kind of potential energy. One is the potential energy between hydrocarbon itself, and the another is the potential energy from pore wall to those hydrocarbon. For the free phase and for the potential energies of free phase, as we can see, the pore wall exactly do not have much effects on that, and the most potential energy is contributed by the hydrocarbon itself. However, for the bulk fluid, we can see the potential energy for bulk fluid is kind of have absolute greatest absolute values than the free phase. So that means the density values of free phase is lower than the bulk. Yeah. And then we go to the next slide to talk about some effects of effects that might affect the distributions of characteristic of fluids within those combined phase. So the first is temperature and pressure. As we know, the temperatures and pressure could exert substantial influence on the fluid's property, no matter within the bulk condition or the nanopores, right? See from this cut, high pressure is that as the pressure goes up, the density value, no matter for the lines of absorb phase or the free phase, the density of that goes up exactly. However, we can observe that the shapes of the fluid goes up with the pressure is quite different, because for the Pantene, let's say at 393 kelvins, at this temperature, the vapor pressure for the Pantene is around 0.8 megapascal in bulk phase. So that means in our observations of our pressure range, it already condensed, being as a liquid phase with relatively low compressibility. So it does not change a lot with the pressure. As for the high temperatures, affect the kinetic energies of hydrocarbon within in the nanopore. That means if you increase our temperatures, that means our absorption phase could get rid of the attraction force that exerted by the pore wall, and they could convert to free phase gradually. which inhibit the absorption of hydrocarbon to certain extent. This is why we usually apply the thermal processing as a method to enhance oil recovery in our shale formation. So let's talk about the effects of pore ties. Here we propose here is the pore tie. Here pore tie. There are two pore ties. One is organic pore, and another is cordial pore. Just that I mentioned in the methodology part. Here we can see the pore tie actually significantly affect the hydrocarbons in the short phase, because we can see for these two curve. This is the same pressure density curve for methane and pentane. As we can see for the blue lines, here is for the organic pore in the short phase. It goes up significantly compared to that in the cordial pores. So that means that effects of pore ties or in the upshore phase is the most important that we should pay attention. And also we see the density distribution, the density and pressure curves for the cordial pores and the organic pore is almost same. It's quite similar for the free phase. That's because as we could see from the potential energy for the molecules, we can see the the change in the pore ties mainly affect the hydrocarbon and the pore potentials to some extent, especially for the cordial pore. That is quite negligible for the free phase. So next slide is talk about the hydrocarbon in place is that estimation of the shale formation. After we do that simulation runs, we have some parameter from the density distribution curve, like the densities of the absorption phase and the densities of free phase as well. Also, we have the techniques of each absorption layer, and the numbers of absorption layer could be obtained from the density distribution curve. So we verify. So the mass amounts of hydrocarbon in shale formation is estimated by the volumetry method. The total mass of the hydrocarbon is basically contributed by the absorption phase and the free phase. So we use our data from the MD runs, and we calculate that, use the volumetry method. And here is less some shale rock property for our calculation. So here is the results of hydrocarbon in place estimations by different method. For the method that colored by the red column is the method that we do not consider the confinement. That means during the calculation, we just use one density value, that is bulk value from experiments. So we could see if we neglect the density deviations of hydrocarbon, that would lead to underestimations of a hydrocarbon in place, because we do not take the density packs of absorption into our consideration. So if we only consider that absorption effect, and we ignore the density deviations of a free phase from that bulk phase, that may lead to that may cause overestimations of hydrocarbon in place, because as we mentioned before, the bulk density is larger than that of the free phase density. So here is a slide for the hydrocarbon for the density profiles of a methane. Is a pentane, a different size of pore diameter. As we could see, within this 2 nanometer range, most of the molecule is existing in the absorb phase. Just a little bit molecule appear in the center as a free phase. As we increase the pore size of our module, we see there are more free phase appearing in the centers of this slate contribute to the free phase density. So that means as the pore size increase, our density, our free phase become more dominant, right? So here is the picture for the contributions of methane in the short phase and free phase on the total mass in cordial nanopores. As we see for the 2 nanometer pore size, free phase oil only take place like 16% of oil, and when the pore size goes up, it gradually increase and up to like 77 at the 10 nanometer pore size. So it's like the dominant states of hydrocarbon will change with the pore size. So this is the end of some conclusions. Yeah, exactly. The hydrocarbon in nanopore is exactly like different density value from the bulk condition for sure, and then the density of hydrocarbon in nanopore is affected by like temperature, pressure conditions, as well as the pore types. So if we're neglecting the density deviations of confined hydrocarbon, that will lead to like a wrong estimations of hydrocarbon calculation in place. So I think that is all for me. Thank you very much for your attentions. If any question, please feel free to ask me.
Yeah, thank you, Yifan. Yes, so it was a very insightful presentation. Thank you for that. For the people online, please feel free to type your questions in YouTube chat. Meanwhile, I will start with one. So you did like molecular simulations. So my question will be, how do you compare your results with experiments? Do you manage to have like molecular scale experiments to compare with, or do you use upscaling first and then compare with larger scale experiments?
Yeah. So we before our simulation for run in the nanopores, we should do our simulation with an infinite size of box for our simulation that represent the bulk fluid, right? And we repeat that simulation with gradually increased pressure, and we compare our results like density with the NIST data available online. That is the experimental data, and we, as well as again the pure for pure fluids, we have our PT diagram for sure, right? Online for the experiments, and we compare our result with infinite box, and we compare the density with that. If same, I feel like for our model validation is okay for the simulation run before that introduced to our pore. Yeah.
And then I would have a second question, which is, what would be the interest in using shale rock reservoirs instead of like other types of reservoirs? I mean, is there any effects to have more nanopores in your confinement effects of hydrocarbons, or would it be better to have more nanopores or like a large amount of macropores? Can you comment on this?
Yeah, is that do you mean like we have a bunch of nanopore stacked together?
Yeah.
I don't think that molecular dynamics could deal with that multiple like pores contact with each other. If we want to do that simulation, it's probably better for us to use like a digital rock simulation. That would be better because for molecular dynamics simulation, it's quite time consuming tool to analyze some physical property. Yeah, hope that will help you. Yeah.
I see. Thank you. So we had 2 comments in the meantime. So Beckman, thanks you both for your presentations. And then we have a question from Harry Scott, which we like to ask, which is the difference between phase behavior of hydrocarbon in shale nanopores and bulk free.
I would say that is obviously one of the most important questions for me, because I'm currently working on phase behaviors of hydrocarbon, and the slide that I show is part of my works currently. The answer to that question is absolutely yes, because let's say the painting that I show in the slides, this is the pure fluids, right? And actually the vapor pressures of the let's say pure fluid could be lower than the bulk fluids. That is because, as we see from the nanopores, they are like the formings of adsorption failure near to the nanopore, that they pack tightly near to the pore surface to form like liquid droplets at pretty low pressures. From this views, the fluid in nanopore is easier to be liquefied compared to the bulk phase. So the PT diagrams of pure fluid, it may like shift to the downward compared to the bulk fluids. And actually for the binary or even more complicated Tenero system, that will be more complicated, yeah.
Okay, thank you very much.
Thank you.
So I think we can finish here. If Maddie, do you have any questions first?
No.
No, that's okay. So I would like to thank both our speakers first. Thank you for being here, for representing the China University of Petroleum before InterPore. And and just to conclude, we will have one more session before having the chance to meet in Qingdao. So it will be on the 9th of May, and you will have two talks from Sayed Fourouchi from the Imperial College of London, and Yao Chu from Polab and the University of Oslo in Norway. So keep updated with our next session, and follow the Tea Time Talk team on our diverse social media. So please feel free to keep touch with us at our gmail.com address. And so see you next time for another great session of the Tea Time Talks. And thank you, everyone.
Thank you.
Thank you very much.